this new seminar in the astro-seminar series by Bartos. It is my pleasure today to introduce you to Jaume Puig, who is visiting us from the IFT, Instituto de Física Teórica. And well, Jaume has been a PhD student there. He's been working in the Damasco group together with Miguel Ángel and Viviana Gamaldi, who is also here with us today. And Jaume is going to talk us about multi-TeV dark matter density in the inner Milky Way halo, which is his latest work and publication. So, Jaume, thank you, and the floor is yours.
Thank you for the nice presentation. So, yes, my name is Jaume Puig, and today I want to present you our work about the multi-TeV dark matter density in the inner Milky Way halo, spectrum, both spectral and dynamical constraint. This is a work that is, you can find it on arXiv, this number right here, which has already been accepted by JCAP, and it's a work made by myself and my collaborators Viviana, Daniele Gaggero, Thomas, and Miguel Ángel Sánchez. So first, during this work or this presentation, what I will assume is that dark matter is a WIMP particle. So, and thanks to using this property, so weak interacting massive particles, we know that if dark matter is a WIMP particle, it is its own antiparticle. Meaning that if we have a dark matter particle which encounters another dark matter particle, it can annihilate. This dark matter particle has a mass of the order of GeV or TeV, more or less, and these annihilations can produce different particles, what I call or what we call standard model channels. This standard model channel, these particles produced by the WIMP annihilation could be quarks, bosons, or leptons. In our case, it will be the third boson. And these particles, since they are very energetic particles, they can produce secondary particles, such as gamma rays, neutrinos, or cosmic rays that we can observe in our observatories here on the Earth, with Fermilab or with H.E.S.S or the LST1 in CET. So, since I will use H.E.S.S data, I want to talk about a little bit about the H.E.S.S telescope very briefly. So, we will focus on gamma ray flux observed by H.E.S.S, which is the current generation of imaginary Cherenkov telescopes, CET, sorry. It is located in Namibia, which is a perfect location to observe the Galactic Center. And the H.E.S.S telescope, we know that it has 5 telescopes for this observatory. And what is the motivation of our work? Why I am studying WIMP dark matter particles? Well, thanks to the TeV cutoff detected by H.E.S.S, which is the previous telescope. We have two different previous works working on the dark matter hypothesis, two by Sembranos et al. In 2012 and 2013, and one by Belikov et al. In 2012, which basically they assume only two different things. First, that the flux observed by H.E.S.S or Fermilab, here we have a nice plot, which is the Galactic Center. Basically, this H.E.S.S J1745 to 90 corresponds to the Sagittarius A* supermassive black hole, and it's a region of around 0.11 degrees surrounding the Galactic Center, just the very source of this Sagittarius A*. And in our case, we have the H.E.S.S data and Fermilab data, and assuming that the total gamma ray flux observed, which is this error mass for Fermilab in green and H.E.S.S in red, we can assume that the total flux can be a combination of two different parts. The dark matter flux, well, I will explain a little bit later, and a background, a power law background. We have the background here, this blue dotted line, and the dark matter part will be this red dashed line. And also assuming the thermal cross-section for the annihilation part, we can obtain, better said, they obtain 3 different results. The first one is that constraints can be set on the dark matter density profile. How? I will explain it later. We also have a boost factor needed with respect to a Navarro-Frenk-White profile of around 1000, meaning that if you take the standard approach for the dark matter halo in the Milky Way, you need an extra 1000 in order to explain the data, in order to have this red curve right here. And the question is, well, can this be explained by an enhancement of the dark matter density profile? This question is what I will try to answer in today's talk. So in order to do that, I will make a brief introduction on WIMPs in the detection with gamma rays. Then I will study the 5 regions of interest that we have in the Galactic Center. One of them is the same region as before, and 4 more. Then we will see the different analysis components that we need in order to explain or to model this gamma ray observed flux. Then we will see the spectral results, basically the J factors. And finally, we will compare these J factors with the simulations and dynamical observations of the Milky Way, plus the S2 star orbit, which I will briefly talk in the end. So this is basically the main formula for the indirect detection of WIMP annihilation. We have the dark matter flux, differential flux, it's a combination of different factors, which I will try to explain a little bit. The first one, we have this part here, which is the channels, annihilation channels, what I said before, this dark matter, these particles, standard model particles that are created because of the dark matter annihilation. Then we have the thermal cross section. In our case, we will take the thermal cross section, which has this number right here in those units. This is the value that is needed in order to explain the thermal relic, the relic abundance of dark matter. Then we have the annihilation spectrum, which is computing all the gamma rays that come from dark matter annihilation. In our case, I will use Cherenkov et al. This work in 2011. Finally, we have the dark matter mass, of course, which is the mass of the WIMP candidate. In our case, will be around TeV. Of course, the annihilation spectra is also dependent on this dark matter mass. And finally, the most important factor here is the J factor. The J factor is where the astrophysical information about the distribution of the dark matter distribution is contained. Is where this is encoded and has this following expression. So we have the J factor is the integral over the line of sight of the dark matter density squared. And this squared is quite important. Why? Because firstly, since it is proportional to the dark matter density squared, we want targets with high dark matter density. Of course, in our case, it will be the Galactic Center. The Galactic Center is the very center of the Milky Way halo, where we should expect to have the highest dark matter density in the Milky Way. And also, uncertainties can give big error bars in the computation. Since it is squared, the uncertainty will be quite large. And we do have a lot of uncertainties in the Galactic Center, and more in particular in our region of interest. And why is this? Well, the problem is the dark matter density profile can be very tricky to infer, and depends on the kind of object that we are observing. In our case, we are observing the Milky Way, so we have a rotationally supported object. And that means that present rotation curves like spiral galaxies. In our case, the Milky Way, as I have said. And also simulations can give prediction for the dark matter density profile. But if we take a look at the Milky Way rotation curve, for example, we have this one by Benito et al. In 2019, we have the different data. However, if we take a look at the Galactic Center, very linear part of the Galactic Center, which would be this red line left part of this red line, we have that we don't have much data available. Actually, the first bane starts at around 2.5 kiloparsecs, meaning that we could have a lot of uncertainties of the inner shape of the profile. Taking into account that we are observing a region of around 10 parsecs, 20 parsecs, 50 parsecs, and this is in kiloparsec scale, so we do have a lot of uncertainties. And what is our region of interest? Well, our region of interest will be this 5 regions right here that I'm describing. We have the Bainite region, which I call the VIR, which is this green circle here, centered at the Galactic Center, just at the center of the Galactic Center, corresponding to Sagittarius A star, as I have said before, and it's a circle of around 0.1 degrees in radius. Then we have the H.E.S.S ridge, which is this rectangular weird shape here. It is delimited by the galactic plane, 0.2 degrees, plus or minus in the galactic latitude, and up to 1 degrees, plus or minus 1 degrees in the galactic longitude, with some masks applied. Taking into account that, for example, the Bainite region, it is masked in this ridge region. Then we have the diffuse. The diffuse region is at this, that starts from 0.15 degrees up to 0.45 degrees. And again, it is masked in the Bainite region, which will be, this information will be quite useful for our conclusions. And then we have the halo, the H.E.S.S halo, what I call H.E.S.S halo, which is this red this that we have here, which excludes the galactic plane up to 1 degree in radii. And finally, we have the H.E.S. inner galactic survey, which is another region which I haven't painted here, from 0.5 degrees up to 3 degrees. And what is the problem when observing the Galactic Center? Well, the problem is that we have a source of uncertainty, which is the astrophysical background model. We need to model, or at least take into account, the diffuse emission and also the point sources. Taking into account that the diffuse emission is what in the previous work was modeled as a power law in the previous slide that I showed you before. And basically, this diffuse emission is due to the presence of a charge cosmic ray C, which is confined in the galaxy by the turbulent magnetic field. The sea of cosmic rays can interact with interstellar gas and low energy photons, producing gamma ray flux up to the TeV scale, which is what we observe with H.E.S., for example. And these main interactions are basically synchrotron, Brent-Talon, inverse Compton, and also the neutral pion decay. And here I am showing you a nice picture of this galactic center and the different sources that have been discovered by H.E.S. and also Zuriaga. In our case, the very near region, what I call the very near region, would be this right here, which is this center in Sagittarius A star. So we need two components to model in order to have the galactic center well described. First, we need the dramatic distribution profile, which, as I have said before, there are many uncertainties in the inner 2.5 kiloparsecs. And because of this, we don't know this cuspier port, the profile of the dramatic density. And finally, simulations favor cuspier profile. So we have a hint of what shape it has the dramatic distribution profile. On the other hand, we have the astrophysical background. We can mask the resolved sources because they have been detected. However, for the diffuse emission, it is unavoidable. We need to phenomenology model this emission. A way of doing this, which is called the on-off analysis, for example, is with a background subtraction. Basically, to point at your source, which is called the on region here, and then you move a little bit to a different side, which is called the off region. So the difference between the counts detected on the on minus the off would be your signal, your final signal. However, well, our question is, how can we treat these components in our 5 regions? So first, we need the matter density profile, as I've said before. In our case, I am showing here, for example, the very near region, which has this boundary here, would be to the left part of this side. And we can see here that we have different models and simulations plotting here. What I'm showing here is these solid lines are models coming from simulations. And then Macmillan 17 and Benito 20, which is this blue and brown regions, are coming for dynamical studies, dynamical observation of the Milky Way itself. And we have that in the inner part, from the very inner region to the left, in the inner part, to the right, sorry, in the inner part, there are a lot of uncertainty. We don't know this chord profile, such as this profile right here, or very steep, such as this part here, like the eagle profile. And in order to characterize these profiles, what I will be using is this formula for the dramatic distribution density profile. In this case, it has 5 different parameters, which I will try to explain briefly right now. 3 of them, sorry, are not very important to our purposes, which are first the scale radii, this RS here, the scale radii. This scale radii is of the order of 20 kiloparsec. You can see it here, 20 kiloparsec, 10 kiloparsec. This is way bigger than our very near region of our regions of interest, meaning that, in essence, our study is not able to discriminate, to differentiate between one scale radii or another. It is not important for us. Also, the beta and alpha parameter are the slope for the outer shape of the halo, which again, we are not observing it because we are observing the very inner part, no? Right? So what we have only left is this ρS here, which is the normalization factor of the Dark-matter distribution. In our case, it's given by basically the local Dark-matter density observed at the Earth. And also we have this gamma parameter. This gamma parameter is the inner slope. Basically, if it is cuspy or chord, the profile in the inner part of the galaxy. So as I have said, we need to model the matter density profiles in order to compare the different J factors. with the fitted values. I will explain later how we can obtain this. We will use different models for full simulation observation. And given the uncertainty, we have, for example, this plot here for the local dark matter density profile. Taking into account that the benchmark Navarro-Frenk-White profile would be choosing gamma alpha beta 113 equally to 113, which our main or most important parameter would be always this gamma parameter, which is 1 for the Navarro-Frenk-White profile. And here we have, for example, for the Benito 20 dynamical study and the Macmillan 17 and the different simulations for the dark matter, local dark matter density versus the slope gamma.
So the two are not compatible.
No, they are not compatible.
And they are observing the same.
No, they are not observing the same. Similarly, but no, this is a rotation curve, like an unusual rotation curve for the Milky Way, and Macmillan 17 is dynamical observation differently from a rotation curve. And finally, well, we need also the background model, which is what we're using this Dragon model. So we will use Dragon and H.E.S.S to model this emission, when the spectral shape is completely defined in each region. For example, if you take the very near region, I can integrate this region within this Dragon model, and I can obtain something like this, will be the spectra versus the energy for the very near region with the Dragon model. And in these papers, if you want, you can read them, but basically it shows that it matches the galactic diffuse emission observed by Fermilab. So it is consistent with other observations. So in our case, what I will do is this background model will be modeled by this Dragon model times a B squared factor. This B squared factor is an order 1 normalizing factor, which will be left as a free parameter in our fits. So now what I want to talk about is this spectral results, how we can obtain them, and these 5 region J factors fitted J factors from the 5 different regions. In order to do that, I will model the total flux given by the Dragon model and this normalization factor, and the dark matter flux. I will restrict ourselves to the set channel because it is the best fit for our data, and we will use Dragon to model the galactic diffuse emission. Also, the annihilation cross-section, I will take the thermal relic for a TeV WIMP candidate, which has this value right here. So we have three parameters. We have the B squared factor, the J factor, and the dark matter mass. Using a chi-square analysis, which has this formula right here, we will try to make the different fits. So here we have the case for the very near region and the rings. I will talk first about the very near region. The very near region, I remind you, is this green circle in the center of the Sagittarius A star. We have first the diffuse emission, which is given by Dragon, this green line, for example. And then, in order to explain the data, we clearly see that we need something else. And this something else is, in our case, assumption, the dark matter, the flux, which has this shape right here. We can see that it fits very well the data, and also respects the different upper limits given by H.E.S.S. And the three parameters that we can obtain from this fit are first the dark matter mass, which is around 36 TeVs in our case. Then the B squared is 9.2. This is not relevant. The relevant part is the J factor, which has a value of 2.7, 10 to the 28 in these units, which might not tell you anything. But if you compare it to the Navarro-Frenk-White profile, the benchmark profile for the Milky Way, you see that you need a factor of around 1,000. One over the other, you need a factor of 1,000. So again, we have the same results that in the previous work they had. They concluded with this 1,000 boost factor needed. Also for the reach, we have the same. We have the Dragon model in the reach, which is the green line here, and finally the dark matter part, given this number right here. And finally, also we see that the J factor compared to the dark matter only, the Navarro-Frenk-White benchmark, sorry. Again, we have a boost factor of around 1,000. Also, you can see here a gap in the dark matter mass for the reach. This is because what we did is to fix this number for the different regions that we have observed. Because in the very near region is where we have this bump in the data clearly, and we have this fit value, this fit procedure quite convergent. So we know that these values would be the most precise value for the dark matter mass using our procedure. if you don't believe this and if you want to leave it as a free parameter, we did that and we obtained the same results as before, but with greater error bars. So that is why we can do this, leaving the 36 TeVs. Then we have the diffuse region. The diffuse region, I remind you, is this surrounding the very near region, excluding the very center of the Milky Way. So in principle, since we are not observing this peak or this cascade profile of the dark matter, one might think that you have a region dominated by background. And indeed, this is more or less what we have here. So the background will be this green line, and we only need small amount of dark matter flux in order to explain the flux completely flux. However, if you want to take a look at the 2 sigma region for this fit, is this gray region here, I'm showing the J factor versus the B square parameter for the Dragon model. We have the best fit value, which is this one here, this red dot, and the 2 sigma region will be this gray band region here. And as we can see, it is compatible with J factor equals to 0. This region has the J factor equals to 0. So we can use this as an upper limit for the J factor, meaning that if we're above this value of the J factor, we clearly are not fitting the data very well. And for the halo region and the IDS, what we have is that the H.E.S. collaboration published in those papers in 2011, and then for the IDS, they did an on-off analysis for these regions. I remember the halo region is this red part here, above and below the galactic plane. And as you can see, the source region, which would be the on region, and the background region, which is the off region, are similar. So meaning that there is no excess found in these regions. And we only can put upper limits to the parameters. In our case, what I'm showing here is the 2 sigma upper limits. Above this line will be excluded, and this will be included. And basically, our number that we care about is the J factor, which has this value right here, 2.5, 10 to the 26. In the case for the IGS, we can do the same. The IGS region is this orange region here, up to 3 degrees, starting from the galactic plane. And again, we obtain this number here, 1.7, 10 to the 25 for the J factor. Again, assuming the thermal Rayleigh cross section always in our case. And this is what we can obtain. So I'm showing here the J factor versus the galactic latitude of the Milky Way. So in other point of view, moving vertically in this plot right here, in order to give some sort of what is the maximum shape of the J factor for the Galactic Center. And what I'm showing here also is the different regions. We have the very region in green, the rich in black, the diffuse in blue, halo and IGS in orange. And then to compare it with different dark matter models that I have shown before, I am also plotting the dark matter only part, which is again the Navarro-Frenk-White benchmark profile, and also the one given by Benito 20, this rotation curve of the Milky Way, which have this different J factor. And this is the most important part here. This is a zoom of the region. We see that comparing the Navarro-Frenk-White with the fitted profile, we get 1,000 times difference. But with the Benito 20, perhaps with the most cuspier profile, the one that gives the greatest J factor, we have some sort of convergence, and we will try to see what can we say about this. Before that, I want to show the different comparison with other observations of the same regions. This is the very near region, and this is the rich region, and I'm showing our fitted values, comparing it with Veritas, Magic, and also Fermi-Dynamics. And the most important part is that our model, with our normalization of the background, the diffuse background, model works at lower energy with Fermi-Dynamic data in the same region. So you can see it here. This we already knew it because Dragon model matches the Fermi-Dynamic data. So we already knew this thing. Thank you. And now, what I want to talk about are the constraints of dark matter density profile that we can extract, comparing it with the different simulation and dynamical observation. So again, we need to talk a little bit more about the dark matter density profiles. The first conclusion that we can extract from this plot is first, as I have said before, we need a 1,000 boost factor extra in order to explain the fitted values. Also, in order to do that, we can use two different approaches. We can use generalized Navarro-Frenk-White profile with slopes gamma steeper than the standard Navarro-Frenk-White, which in essence would be the J factor corresponding Benito 20 model corresponding to this value here, or the enhancement of the inner profile because of a dark matter spike in the internal halo. And what is a dark matter spike? What do I mean when I say dark matter spike? So when I say dark matter spike, in order to define the inner profile, I remind you this is in kiloparsecs, so 10 to the minus 2 up to 10 to the minus 10 kiloparsecs. We can take different approaches. We can take the generalized Navarro-Frenk-White profile, which is the formula that I showed before, which is alpha, gamma, beta parameters. No modification of the profile. This solid line here, this would be the Navarro-Frenk-White profile, this solid line. Also, we can take the adiabatic spike on the black hole, which is, I will explain later, but basically it allows the maximum dark matter, the maximum peak of dark matter density, which is this dashed line right here. The better shape is that you have a generalized Navarro-Frenk-White profile, and once it gets to the 10 to the minus 2, 10 to the minus 1 kiloparsec, basically 50 parsecs, it changes to this slope right here. Also, you can take into account the adiabatic spike, plus the interaction with the stars, meaning a heating of the dark matter particles. This flattens the spike a little bit and changes the slope of this dotted line. And then you can also take into account the extreme case of the instantaneous spike. This is the extreme case of the instantaneous form of the supermassive black hole H.E.S.S star. This would be as a way of putting a lower limit for the dark matter spike, which is this dot dashed line here. Right, so for the generalized Navarro-Frenk-White profile, again, extrapolation of the external profile up to the inner region, we have these different plots for the different regions. What I'm showing here again is the J factor in vertical axis versus the gamma slope in the horizontal axis. This gamma slope is this gamma, the inner slope of the profile. And here, the most important plot is the one given by the perihelion region. We have the fitted values in horizontal, green, rich, perihelion region, rich, diffuse, and halo. And also the different J factors computing with different models. We have Macmillan 17, this blue region, Benito 20, this brown region, and the different simulations coming from the different studies. And in our case, you can see here the excluded words written in every single plot. Because if you have a dark matter J factor integrated using the formula, that it is above the fitted values, it means that the theoretical gamma ray flux created by this density, by this dark matter, would be above the one observed by H.E.S., meaning that indeed we can exclude it. Otherwise, it would have been observed. So if you cross these lines, you can exclude your model. In our case, our crossing point for the perihelion region is at gamma equals to 1.3. So the generalized Navarro-Frenk-White profile can be excluded up to 1.3 for this slope, for the inner slope. However, if you take into account the rich, diffuse, and halo, nothing can be excluded. And this is because these different regions do not take a look at the inner part of the halo, so the cuspiness of the profile is not important in those regions. That is why we are always below the upper limits. For the case of the adiabatic spike, you need to assume three things. The adiabatic growth of the supermassive black hole Sagittarius A star, first thing. The second, you need central position of Sagittarius A star during its whole formation, so it's always in the center of the Milky Way, and no major mergers during the last 10 gigayears. If you take into account this, and following this paper by Condolences in 2013, you can obtain these profiles right here. So we have basically, sorry, I will move. We have the external profile in the outer shape, which is this part right here. And then once it gets to a radii of 10 parsec or 50 parsec more or less, the slope, the profile changes up to the generalized Navarro-Frenk-White, changes to this spike profile here. Basically, the slope, the gamma, changes to gamma spike with values of 2.2, 2.5. I remind you that the gamma, the slope is around 1 always. So it's quite a change. And then once it has the same shape, which is right here. Once it gets to this value, to this density saturation value, it changes again the slope up to 1.5. And this is because we are assuming annihilating dark matter. And because of this, if you have too much dark matter, it will annihilate and it will erase the peak. And this too much dark matter, this threshold, is given by this Rorschach value, this density saturation value, which is the dark matter over the age of the black hole, 10 gigayears, times the annihilation cross section. And with the adiabatic spike, the same plot as before, but with the J factors completed with the adiabatic spike approach, what we have is that in the very near region, we can exclude everything, or almost everything. We are several orders of magnitude. This is 10 to the 28, more or less. This is 10 to the 33. So we can exclude all of our models following the adiabatic spike approach. However, and this is very important, in the diffuse, halo, and rich, nothing can be excluded. And this is because the regions, the regions is defined such as, well, it's not defined, but it coincides, such as the spike radii is inside the mass, inside the mass of the diffuse and the halo, meaning that these regions do not observe the spike. Therefore, the J factors are not enhanced by the matter spike. This is what I mean. And also, the gamma ray part coincides with this information because it's always below the upper limits. And this will be very important in my conclusions at the end. What I was basically assuming until now is that the supermassive black hole Sagittarius A star is static. If you want to include the rotation of the supermassive black hole, Sagittarius A star, what you have is, for example, the different dark matter density profiles here. So you have the initial profile, which will be the generalized Navarro-Frenk-White profile, this red line here, and then once you want to grow at the adiabatic spike, you get this slope right here. We have first the adiabatic spike not relativistic, which is the first approach, which is this green line here, following this blue again. Then we have the adiabatic spike relativistic approach, which is the one that I'm using always in order to compute the adiabatic spike, which is this purple line. And if you include the rotation of the black hole in the metric, what you obtain is the same profile a little bit further in the inner radii. Note that it is in units of Schwarzschild radius, so the change here is not very visible. And actually, if you want to compute the J factor up to 1 degree interrelation angle for the whole matter density profile, you obtain a factor of 2 or even lower than 2. And this difference also mostly disappears when you take into account the annihilation of dark matter, meaning this saturation value of the dark matter density, which would be around more or less here. It is not showing this picture. And basically, what I want to say is that this factor of 2 is irrelevant for our purposes, because if we compare this factor of 2 to the different uncertainties that we are taking into account in the Benito 20 model, Macmillan 17 model of the different models, it is lower than our uncertainty. So we can just ignore this part, okay? Take into account that this example made by Ferrer in 2017 is for a H.E.S.S profile, which just has gamma alpha beta parameters of 114. I remind you that the Navarro-Frenk-White, the benchmark profile has 113. However, we are observing the brightest part of the galaxy, so the alpha beta part is not very relevant to us, only the gamma. Since the gamma are equal, it generates the same adiabatic spike, the H.E.S.S profile and the Navarro-Frenk-White generalized profile. And finally, we have we have 2 more left. One of them is the star spike profile. The star spike profile, what it assumes is the adiabatic spike as before, the same assumptions as before, but also the scattering plus the heating of the matter particles because of the stars. Following these papers, these 2 papers right here, and what you get is a flattened adiabatic spike. Basically, we have the same shape as before. We have the generalized Navarro-Frenk-White profile up to this spike radii of 1050 parsecs. Then it changes to the adiabatic spike profile, which is, you might not be able to see it, but it's this part here, the change of the slope. And once it gets at 2 parsecs, the slope, this gamma spike slope, changes to 1.5. note that this gamma spike is 2.5, 2.2. So in our case, if we want to show the different upper limits, the different factors computed with this approach, we obtain this plots here. The most important one for our purposes will be the perimeter region. We have that now the crossing point is around 0.8 for the gamma, for the slope. And we have that, okay, so from 0.8 upwards, we can exclude the matter density profile. Now, if we go to the bridge diffusion halo, as before, everything is under the fitted and upper limits value. And finally, instantaneous spike. This is in order to put a lower limit of the dark matter spike in the Milky Way. This is the extreme case of instantaneous growth of the Sagittarius A star. Of course, this is not a real case. In our case, for the shape of the halo, we have generalized Navarro-Frenk-White profile as before. Then, once it gets to a radius of 10 to 90 parsecs, this has to be computed numerically, following this paper, Ulio et al. In 2001. We have that the change of the slope from gamma to gamma instant, which is 4/3, a little bit bigger than 1, greater than 1. And finally, once it gets the saturation density, it changes again to 1.5, as before. And for the instantaneous spike, showing the J factor versus the gamma, here we have that the crossing point for the excluded values is around 1.2. So a little bit greater than the star's spike. And we can plot the best profile, this crossing point that I was saying before. So these are the profiles following the Benito 20 dynamical model. We have the Navarro-Frenk-White profile with gamma equals to 1.3, the generalized Navarro-Frenk-White profile. I remind you, this is the solid line here. Now, if you want to take into account the star's spike profile, you would get a slope of 0.8, which is this dotted line here, quite similar to before because they have the same J factor, so it should be similar, the density. And finally, we have instantaneous spike, which is this dashed line here. You might not be able to see it, it's quite similar to the generalized Navarro-Frenk-White profile, basically because they have the same slope, the inner slopes. And note that the adiabatic spike is completely ruled out, so we cannot paint the equivalent profile for the adiabatic spike. And you can see here an excluded region here again. This means that if, for example, you have a dark matter density profile, which is, I'm making this up, which is like this, above these lines, it means that the computed J factor would be greater than the fitted value. And because of this, as before, we can exclude it because the theoretical gamma ray flux would be greater than the fitted values again, than the observed value, sorry. So we can exclude the shapes of the dark matter density profile, which are greater than these different slopes. And I was saying before that the diffuse region was very important to us because of this. Because with the adiabatic spike, the star's spike, and the instantaneous spike, they have the same constraints as the generalized Navarro-Frenk-White profile. What does it mean? What does it mean? It means that for the diffuse region, which I remind you is a region center of the Sagittarius A star from 0.15 degrees up to 0.45 degrees, it means that because we have the same constraints, the spike radii of the dark matter density profile should be also smaller or of the order of the diffuse region, which is 0.15 degrees or 0.45 degrees. If you want this in parsecs, it means from 22 to 65 parsecs. But in order to get to these two conclusions, this spike radius of 22 up to 65 parsecs, and also excluding the adiabatic spike, we need to assume WIMP dark matter, set channel, and semi-relic cross section. We need to assume a lot of things. So the question is, can we relax our hypothesis? Can we go to a non-hypothesis at all? So in order to do that, it is where the S2 star orbit comes into play. So the S2 star is a star that rotates very near to the Sagittarius A star. Actually, the radii is of the order of parsecs. So again, of the order smaller than parsecs, actually, sub-parsec. And from the S2 orbit, following papers such as Gravity 2020 or Gravity 2021, we can set constraints on the extended mass within the orbit. So the integrated dark matter mass within the orbit of the S2 star. And this is because of the precession of the orbit of the H.E.S. orbit that can be observed with these telescopes. And this analysis is independent on a particular dark matter theory. You only need a dark matter halo inside the H2 orbit. We don't need a lot of hypotheses. So in order to do that, what we have is, okay, these papers, Gravity 2020, Gravity 2021, and Doe et al. In 2019, they say that the maximum extended mass, the maximum integrated mass of the dark matter halo is this one for the different papers, up to a certain radii, which is 10 to the -2 passes actually. And if you have a dark matter density profile, which integrating it in order to get the mass, which crosses these upper limits, you can exclude the dark matter density profile. So following this idea, what I'm plotting here is the adiabatic spike and the stars spike. With the adiabatic spike, which I remind you is the maximum spike, the greatest spike that you can get in the Milky Way, you can more or less rule out some of these models. However, if you go to the stars spike, nothing can be ruled out. Actually, the same holds for the generalized Navarro-Frenk-White profile and for the instantaneous spike. You can only rule out models with the adiabatic spike. And note that if you have an adiabatic spike, you might not be able to see this, but from your point, but for example, the Macmillan 17 with gamma equals to 1, which means basically the Navarro-Frenk-White profile, or the yellow line, which is Navarro-Frenk-White profile as well, you have that it crosses this excluded region, and therefore you can exclude the adiabatic spike within the Navarro-Frenk-White profile. We can plot it here, which is nicer and better to see. What I'm showing here is the maximum spike radii for a given model, for a given slope of the profile, which is this gamma slope, following Macmillan 17 or Benito 20, Macmillan 17 on the left, Benito 20 on the right. The maximum spike radius allowed by this dark matter, by this extended mass observed by the H.E.S. orbit, by Gravity 2020, for example. So you have this, you have that the maximum spike radii is given by these curves right here for Gravity 2021 and Gravity 2020 and Doe et al. 2019. And you have a model that has a spike radius that crosses these lines. You can exclude it because of the same logic as before. So here we have that the crossing point is around gamma equals to 0.8. Here is gamma equals to 0.8. And if you take into account the Benito 20 benchmark instead of Macmillan 17, what you have is that the crossing point is around gamma equal to 0.6 in order to exclude the dark matter adiabatic spike. So as a final conclusion, we have that the fitted value for the TeV WIMP particle for our candidate is 36 TeVs, assuming always the thermal Rayleigh cross section, which has these values here for a TeV candidate. We have a conservative approach. We are only able to exclude profiles with a J factor greater than the fitted values. Only this. We only exclude profiles with a J factor greater than the fitted values, as before, and the diffuse region. Thanks to this region, if a dark matter spike exists in the galactic center, it is required to have an angular dimension of the order of 0.15 degrees or 0.45 degrees. This 22 up to 65 parsec that I was telling you before. Also, a filter analysis is required in order to constrain this error bar a little bit better. So now, if you compare the final constraints of everything that we have talked about until now, we have that for the generalized Navarro-Frenk-White profile, we can exclude profiles with gamma up to 1.3. The adiabatic spike is completely excluded. Then the stars spike can be excluded up to gamma equals to 0.8 more or less. And for instantaneous spike is up to 1.2. Now, if we move to the H.E.S. orbit, we can only exclude the adiabatic spike up to 0.6. So finally, I want to talk about the Cherenkov Telescope Array, which would have and will have a greater sensitivity and angular resolution than H.E.S., so it should be able to answer this question with better results. It has two locations in La Palma on the northern hemisphere and the Parallel Desert in Chile in the south hemisphere. And if you want to compare this to the H.E.S. telescope, the H.E.S. telescope is this yellow line here. So it is the CET expected flux sensitivity will be 1 order of magnitude better. And also the angular resolution, which is quite important for us in order to distinguish these spikes. The CET angular resolution at around 1 TeV will be 0.05 degrees. If you want to compare it with the H.E.S. angular resolution, which is not shown here, but you will have to believe me, it's around 0.1 degrees. So it's twice as good the angular resolution. And this will be all. Thank you very much.
Thank you very much, Jaume, for your next talk. We have questions from the audience.
Thanks for the impressive talk. I'm really wondering about how the shared black or changes the density of distribution for the WIMPs.
It changes because, yes, it changes because the metric is different. The static metric for the Schwarzschild black hole is different than the Kerr black hole. So because of this, the WIMP distribution changes. With WIMP, any dark matter particle doesn't have to be WIMPs, and actually it is a function of the spin. So this final difference of 2 is when you have the maximum spin available, which is not 1 will be the maximum spin, 0.98, I think, for these two values. If you have less spin, these 2 changes to 1. So it's not. That is why we can ignore this this correction.
What are the explanations for this cutoff?
You mean cutoff of what?
The H.E.S. cutoff. I mean, right? You have tried to explain it with the matter, right? But are they are the explanations.
Yes, you can have millisecond pulsar, for example, which have a similar shape of the dark matter part, but I think this is only for the TeV range. This is our TeV range in our case, and it's a different explanation for the H.E.S. cutoff. I only know the dark matter, so you have to forgive me. But our point here is, since these upper limits are respected with the Dragon model, we are in a consistent check, if you want. So we know that, at least as far as we know, this should be or can be an explanation. Can be an explanation, not should be. Can be an explanation.
And another question: can you show the results of your fits when you were fitting the dark matter contribution?
Sorry.
Yes. Yeah.
Okay.
So, is it correct me if I understand it right or not? It's suspicious that the V square parameter changes with the region that you are fitting, because it means that also you need a less like a substructure of baryonic matter also in the.
Yes, it's a good question. Yes. Two things that I want to say. First, for the case of the diffuse and the rich region, I remind you that these two regions are more or less coincident in space. See that this blue disk also is in the same region as the rich part of the rich. So the V squared of these two regions should be equal, or at least on the same error bar. And here in this plot, we have the diffuse V squared, the J factor and the V squared diffuse, and this is the best fit for the rich. So we are within the 2 sigma. So this, we know that at least for the rich and diffuse is more or less consistent. However, if you take a look in the VIR, for example, in the Brownian region, the V squared is 9, and this is 0.3, 0.5, 0.8. Well, the first thing is that the normalization is different because the region is different. It's not coincidence. So we can more or less do this. And also, the Brownian region is very, very small region. This is 0.1 degrees in radius, meaning that for the case of the Dragon model, for example, I think we only have 1 or 2 pixels within it. So that is why we have this big uncertainty on the V squared. Also, and this is
I mean, the errors that you write.
Yes. They are not so big because the fit is quite good for the Brownian region, because we have the data very well explained by all of this. But I mean uncertainty. Sorry, I meant big number of V squared, not uncertainty. But if I want to talk about this V squared parameter, why we can use the V squared parameter? Well, I remind you that with sorry, I forgot what it is. that with Fermilab, with this 9.2 B² parameter, we are following this Fermilab data. So again, another consistency check with different telescope and different energies. And in order to explain this B², I have a slide, a backup slide, nearing the end. Yes, here. So the reason of this normalization factor is because of this poor knowledge of the different conversion factor between the CO emissivity and the H2 molecular gas column, which is the main, this gas column, this H2 molecular gas column is the main component of this dragon model. So, and this factor basically scales linearly with the diffuse emission, with the dragon emission. If here I am showing the different components of the dragon model, and the total part for the very region again, the total part is this blue black line, this total part, and the H2 component of the molecular gas is the same. So the problem is that this molecular gas is very hard to estimate the density. So having an uncertainty in this normalization factor of the H2 basically translates into an uncertainty of the maximum total diffuse emission for these regions. So it's a way of putting into an uncertainty this part, this H2 molecular gas column.
So, if you don't mind, Antonio, I have a follow-up question concerning the dragon model. So, how compatible is it with Veritas observation of the galactic ridge?
Yes. Well, I have shown actually the plot, which is it is sorry, should be a little bit here. This is the galactic ridge, and Veritas, I think, this is the yellow part. So it is compatible, but not by much. Here you can see that it has a different. Yes, it's a little bit bigger than the H.E.S. and also MAGIC observations.
But it's a problem of the experiments. They are not compatible. It's not a problem.
Yes, also Veritas here has a different. Yes, it's bigger actually than MAGIC.
The dates are also different. So.
Yes, yes. Well, this is the data that I was able to gather.
Simultaneous observations. So
because
who knows if it's more active for whatever reason.
Yes, this is published data, so I am not in Veritas or in MAGIC, so this cannot be like. Yes.
So I think we have time for last question.
Benito profile.
Benito's profile. Yes.
What's the difference with Navarro-Frenk-White?
Yes. So when this, sorry, I think is no, I forgot this here. This Benito 20 profile. The idea is, no. The idea is to use the Milky Way rotation curve. Actually, the plot that I showed at the beginning of the rotation curve is the previous paper of Benito 20, Benito 19 would be. And what they did is, you know, getting this rotation curve of the Milky Way, and then you fit the different models in order to explain this data. So you change the slope from 1.5, 1.3, sorry, let's call it 1.3, from 0 to 1.3 of the gamma. And then you also take into account different square radii and normalization factor and everything. And the best fit is this one corresponding to this one. Well, this will be here inside these two regions, 1 sigma and 2 sigma, the different colors. And if you want to compare it to the Navarro-Frenk-White, well, the Navarro-Frenk-White profile, what it tells is only the slope, which is gamma equals to 1. So it will be this vertical line here. So this will be like this. So you can see that in order to explain with Benito 20 and Navarro-Frenk-White profile, what you have is a normalization, the local thermal density normalization factor should be greater than, let's say, different models. This would be the one of these based on Navarro-Frenk-White profile. You can compare it. It's more or less twice as big. Yes.
All right, thanks. Let's check if we have any questions on Zoom.
There are no questions, and we are running out of time, actually.
Okay. Thanks, Enrique. Then I think let's thank Jaume again. Close the session now. Thank you, everybody.
Thank you.
Thank you, Enrique.